Alright, we're going to conclude section 15.3 in this video, and we're going to work on exercise 9 on page 1021. Which says, suppose that f, g, and h are continuous functions. Prove that the line integral over c of f of x dx plus g of y dy plus h of z dz is independent of path. So what we're going to look at first is we're going to look at the curl of the vector field. So first, what is the vector field that we are considering here? So f of x, y, z is equal to f of x, because this is m, n, and p, because that's the dx, dy, and the dz. So f of x, g of y, h of z. And we were told that all these are continuous. Now let's look at the curl, and when we look at the curl, we'll see the partial derivatives of each one of these. So the curl of f jk, partial with respect to x, partial with respect to y, partial with respect to z, f of x, g of y, h of z. And here it's important that we write the x, y, and z in there, so we don't think that they're telling us explicitly that f is really just a function of x, g is just a function of y, and h is just a function of z. So we end up with the partial of h of z with respect to y is 0, minus the partial of g of y with respect to z is 0. That's our I component. And our j component, the partial of h of z with respect to x is 0. The partial of f of x with respect to z would be 0. And then plus our k component, the partial of g of y with respect to x would be 0. Then minus the partial of f of x with respect to y would be 0. So all of our partial derivatives are 0. So n 0 is is a constant function. So all our partials are continuous. And then we see that our curl is equal to the 0 vector. So all the conditions are met that our functions are defined everywhere, or that's when they're telling us that they're continuous. And then our partial derivatives are all continuous, and our curl is the 0 vector. So those things give us that f is independent of path. So not f, the line integral over c, excuse me. The line integral over c of, we can rewrite this now as f dot dr. This is the same as that up there, because we've defined f to be this, is independent of path. Alright, so next we'll look at number 14 on the same page, which says the force f of xy exerted at the point xy by a two-dimensional linear oscillator at the origin given by the vector field f of xy equals negative ax, negative ay. Where a is a positive constant. Find the work W done by the force on an object that moves from 3, negative 6 to 1, negative 2. Alright, this tells us a was greater than 0, and we're going from 3, negative 6 to 1, negative 2. Oops, sorry. 2, 1, negative 2. All right, and we're computing the work here. So W equals the line integral over C of f dot dr. All right, so now, but we don't have a curve C. So what we're going to do is we're going to go through and see, is this independent, would this be independent of path, excuse me. All right, so here, let's do the curl. The curl of f will be the partial of n with respect to x minus the partial of m with respect to y times k. This will be 0 minus 0, so this is indeed the 0 vector. So now let's see if we can find a scalar function f such that the gradient of that scalar function is this. So we're looking for negative ax comma negative ay to be equal to f sub x comma f sub y. So you pick whichever one of these you want to. I'll do the f sub x one. So f is going to be the integral of f sub x, which is the integral of negative ax with respect to x. And that's going to give me negative ax squared over 2 plus c. So negative a over 2 x squared plus, sorry, not c, plus a constant integration. We're integrating with respect to x, meaning we're treating y as a constant. So our constant integration can be a function of y. So we have f equals this. So we're going to take its partial. We already used that. So now we're going to take the partial of this with respect to y. So f sub y equals, that's just going to be 0. And then this would be h prime of y. But we know that f sub y, the partial of f with respect to y, is supposed to be this. So that means h prime of y. So h prime of y has to be equal to negative ay. And now we integrate both sides of this, and we get h of y has to be equal to negative ay squared over 2 plus, now this is actually going to be a numerical constant c. So let's say negative a over 2 y squared plus c. So now we take this and we put it in right there. So this goes right there. And now we have our function f. So f of xy equals negative a over x squared minus negative a over 2, x squared minus a over 2 y squared. So just negative and then plus c. I'm going to take my c to be 0. You can take your c to be whatever you want it to be. So this is negative a over 2 times x squared plus y squared. And now to evaluate our line integral, we're just going to evaluate this at 1, negative 2 minus this evaluated at 3, negative 6. So W equals the line integral over C of f dot dr, which is going to be our scalar function f evaluated at 1, negative 2 minus f evaluated at 3, negative 6, which was negative a over 2 times 5, and then minus negative a over 2, so plus a over 2 times 9, 45. So we get 45a minus 5a. We get 40a over 2, which just gives us 20a. And that will be our answer there. All right, so that concludes section 15.3, and we'll start section 15.4 in our next video.